Okay, for the last question, question 5, we are given this particular structures, which is the safety barrier, and it actually have a cross-section area which is a trapezium. So the very first part, and all the information are actually given on the diagram itself. So for the very first part, okay, we are given that you have a fixed volume, okay, of 0.8 meter cube. You have to show that the area of the external surface area of the barrier, okay, is of such a formula. So the very first thing will be, let us find what is the external area. So first thing is, this length is 1, this length is x, means that this slanted length is actually 1 plus x squared using square root, using Pythagoras theorem. So the area, okay, with this, I will be able, okay, the next thing that you may also need is the area of this cross-sectional trapezium area. Now, if you recall the formula for the area of trapezium, this particular red area, okay, is actually equals to half of the sum of the two parallel length multiplied by the height, which is 1. So it will give you 2x, okay, the area itself. So the area A will be equals to, okay, 2 times the red area plus the slanted area, 2 times the slanted area as well because there's 2 sides, plus the top area plus the bottom area. Okay, simplify a bit. We'll have something like this. Okay, but take note that the question, okay, actually want you to show that the A is only in terms of x, and that is where this information come in. You know that this barrier itself have a fixed volume of 0.8 meter cube, which basically means that volume, which is equals to the cross-sectional area, which is the red color area, multiplied by y is equals to 0.8. Okay, 0.8 is actually 4 over 5. Okay, we can actually maybe keep it like this for the time being. So this will implies that the y is actually 0.8 over 2x equals to 0.4 over x. Okay, so now I can actually put it in. .4 over x square root 1 plus x square, okay, plus 4x 0.4 over x, which is actually equals to 4x, okay, give or take, I found part of it already, plus 0.8 square root 1 plus x square over x, plus cancel 1.6. And hence, with this, we will be able to find the expression for A, which is the total external surface area of the barrier. Okay, for the next part of the question, part 2, we are supposed to use differentiation to find the value of x, which will give the minimum value of A. Now, using the equation that we have just now, okay, we will go and find dA dx, set it to be equal to 0, and from there, we'll be able to find the value that will give us the minimum value of A. So what I do is, this is the equation, so dA dx is equals to 1.6 a constant, so 0, 4x is like this, okay, 0.8, I will actually keep it outside. I see a quotient, so square the bottom, hold the bottom, differentiate the top, minus hold the top, differentiate the bottom. So do some tidying up. Okay, I pull the x square out. Okay, sorry, miss out a minus half here. So x half x times 2x will give you x square. Now the minus half is actually can be put in the denominator. Now this means that I can actually do more simplification so that later when I set dA dx to be equal to 0, the value of x can be more easily found. Okay, double check, yes. So 4 plus 0.8 x squared will give me minus 1, 1 plus x squared half. Okay, so this will means that this is the A dx. So for A to be minimum, I will actually have to make the A dx equal to 0. This will imply that equals to 4. So to solve for x, I have to actually square both sides. Now this is actually equals to 0.2. So squaring both sides, which means that the equation I need to solve is x6 plus x4 minus 0.04 equals to 0. Now if you return back to the questions, you can see that you only need to actually find the value of x with no exact, okay, the wording exact there, which means I don't need to solve it algebraically. I can always use my GC for help. So what I need to do is, okay, let's quit out. Okay, so go to apps, go to poly simultaneous solve. So poly root finder, order 6. So everything is correct other than this, negative 0.04, enter. So solve it, takes a few. Okay, now then the thing is, usually for these type of questions, you will definitely, if you use GC to solve, you will definitely get 6 values. Now the thing is that if you actually get 6 values, the reason is that the GC actually even find the complex roots for you. So for all those I, okay, these are all the complex roots, you don't need to actually care about it. Then this is the 2 values that you need to actually look at. But because of the fact that the x is actually positive, this is a practical question, okay, the length must be positive. So you know that the answer must be 0.428 of it's 0.429. Okay, so this implies that x equals to 0.429. Okay, and do a check. For x, so the dA dx, okay, will be 0, positive, negative. Okay, no, it's actually negative, positive. So therefore at x equals to 0.429, A is minimum. Okay, for the very last part of this question, we are actually looking at the rate of change of volume, okay, due to thermal expansion. It is observed that as the safety barrier expands, only x vary, while the dimension of y remains unchanged at 1.5 meters. Now what this is trying to tell you that if you return back to what we actually did just now, we actually know that, okay, it's not here, it's here. We actually know that the volume actually looks something like this. V equals to 2xy, okay? Now, but because of the fact that we actually know that the dimension of y remains unchanged at 1.5 meters, this means that V is actually equals to 3x. Okay, V equals to 3x. So once you read the questions, okay, we are given that we know the rate of change of the volume is 0.01, okay, meter cube per hour, and we are also given dA dx equals to 11 meters. Okay, later we will check what is the use of it. However, we are supposed to find the rate of change of x. So if you look at this, this means that in order to find the rate of change of x, I can link up all the information I have right now. I have dV dt. This means that I can link it up using this, with this as my target, dx dt. So dv dx is actually very fast, it's actually 3, so 0.01 equals to 3 dx dt, which means that my dx dt is equals to, okay, let's see whether I can make it into a very nice number. This is 1 over 100, so this 1 over 300, okay, meter, okay, per hour. And to actually find the rate of change of A, you actually need dA dx times dx dt. Just so happens that the question is so kind enough to actually give you dA dx, hence I can actually immediately find the answer as dA dt is 11 over 300.